Hi, I'm Borna, your organic chemistry tutor, and in this video I'm going to be talking to you guys about how to choose mechanisms between SN2, SN1, E1, and E2 and how to draw the product. Now, given the fact that a lot of these reactions share similar conditions, it could be a little difficult to choose the right mechanism and draw the right product. In this video, I'm going to show you guys a method that you could apply step by step to choose the mechanism and draw the appropriate product. And finally, I'm going to do a bunch of examples, so stay tuned until the end of the video. Let's get started. Okay, so I understand that sometimes it could be challenging to determine the mechanism of a reaction between SN2, SN1, E1, or E2 and determine the product. But I'm going to show you guys a process that I use to determine the mechanism, and I'm going to use an example to break that down, and then I'm going to apply that to a lot more examples. Now, the difficult thing is that this can sometimes not be as clear-cut, but I've chosen examples that are kind of clear-cut, and I hope to be able to make my point. Alright, so I'm given this reaction. I'm asked to draw the product and determine the mechanism for the reaction. Okay, so the first thing that I'm going to do is that I'm going to look at the substrate, the thing that has the leaving group on it. I want to make sure that it has a good leaving group. It has a Br on it, which is a good leaving group, so it does have a good leaving group. And not that it affects any of these reactions any different than it does the others, like a good leaving group is necessary for SN2, SN1, E1, and E2. But if you have a poor leaving group, that might be a no reaction situation. The next thing that I want to look at is that I want to make sure what kind of alkyl halide or substrate I have. This is a primary alkyl halide, so I have a primary substrate. And the reason why that is important is because that can limit the choice of mechanisms that I have. For instance, I know that primaries and methyls, they cannot form carbocations, so no SN1 and no E1. On the other hand, I know that tertiaries cannot do SN2, for instance. Now that I have a primary alkyl halide, SN1 and E1 are out, so it's between SN2 and E2. Can it do elimination? Meaning, is there a hydrogen adjacent to the leaving group? Yes, it can do elimination, so we cannot rule out E2 at this point. The next thing that I want to do is that I want to look at the nucleophile / base. In this case, it is CN-, which is a very powerful nucleophile. There are tables that you can consult to be able to kind of determine whether something is a weak or a strong nucleophile or a weak or a strong base. I'm going to try to give you as much information in this video as I can, and I'm going to try to make a video in the future, and I'm going to leave a link to that, to explain how to rank nucleophiles and bases based on their nucleophilicity and basicity. So it's a pretty strong nucleophile, but it's not a strong base. The reason why this is a good nucleophile is because it has a negatively charged carbon. It's pretty diffused. It has a lot of polarizability, so it can be a pretty good, pretty efficient nucleophile. Not a very strong base. Not a very strong base. Does it have steric hindrance? Not really. Steric hindrance is particularly bad for SN2. So if the base / nucleophile had a lot of steric hindrance, at this point I would have said that it was going to be SN2, but it doesn't. Solvent temperature. Well, the reaction arrow doesn't say anything about the temperature, but it's using a polar aprotic solvent, which is good for both SN2 and E2, so that doesn't tell us anything. And then at the end of the day, I'm gonna basically compile the information that I gathered and basically determine a mechanism based on that. So step 4, we have to determine a mechanism and determine the product. So we have a primary halide with a good leaving group, and we are combining that with a nucleophile that is a very strong nucleophile, but it's not very strongly basic. Now, if you have a nucleophile that is weakly basic, that is going to be an SN2. And what is going to happen is that the CN is going to come in, kick this out, and let me erase all of these arrows and whatnot. And then at the end of the day, that is going to give me a substitution product. Like this. Now let's apply this to an example. Okay, this is the next reaction. So it does have a good leaving group, no problem there. Alkyl halide is secondary. Can it do elimination? Yes, it does have alpha hydrogens. So we cannot eliminate any mechanism really. Secondaries can do SN2s, E2s, SN1s, E1s. So we don't really learn anything from there. How is the nucleophile slash base? It's a very strong nucleophile, not strongly basic. Because N3 minus, strong nucleophile, because does have negative charge. It is pretty polarizable, but it's not very strongly basic because HN3 has a pretty low pKa. Doesn't have steric hindrance. So all of these so far favor a substitution reaction. I have a very strong nucleophile, but it's not very strongly basic. And strong nucleophiles and bases tend to want to do SN2, E2 as opposed to SN1 and E1. They don't allow for the carbocation to form. Look at the solvent and temperature. Solvent is polar aprotic. Now see, none of these factors in and of themselves dictate a mechanism, but a combination of these factors favor a certain mechanism over another. Now step 4, I have to determine the mechanism. I have a secondary substrate, could do any one of them, but I'm combining that secondary substrate with a nucleophile that is not very basic. It's very strongly nucleophilic, doesn't have much steric hindrance, and I'm doing the reaction in a polar aprotic solvent. So it has to be SN2. It's not going to be E2 because my nucleophile slash base is not very basic. It's not going to be SN1 or E1 because I'm using a strong nucleophile, and I'm doing the reaction in a polar aprotic solvent. So it's going to be an SN2 reaction, inversion of configuration, and this is going to be the product. Next reaction. All right. Looking at the substrate, it does have a good leaving group, so it's not going to be a no reaction situation. The substrate is secondary, so I cannot rule out any mechanism at this point. It can do elimination because it does have alpha hydrogens, or rather beta hydrogens, sorry, next to the leaving group. And now I want to look at the nucleophile slash base. It's just MEOH. A lot of people would think that it's Me plus OH minus, like that is not the case. It's like CH3OH, it's methanol. It's an alcohol, it doesn't dissociate. So it's like CH3OH. It's a very weak nucleophile. It's not negatively charged, and it's a very stable molecule. It's a very weak nucleophile and a very weak base. It's, I'd say, probably equally nucleophilic and basic. It's not particularly basic or nucleophilic. I mean, it's not either of them. Does it have steric hindrance? Not really. And, well, we're heating that up, so there's a little bit of heat. Plus a polar protic solvent. Alright. So step 4, let's determine the mechanism. Let's put all the information together. So we have a secondary alkyl halide combined with a weak molecule that is not particularly basic or nucleophilic and doesn't have a lot of steric hindrance. And the nucleophile slash base slash solvent is a polar protic molecule. All of these conditions push us towards SN1 and E1. Usually you're going to get a mixture of these, but probably mostly SN1. The only conditions under which you're going to get a significant amount of E1 reaction, we're going to have an example of that coming up, is going to be dehydration of alcohols. Now, what is going to happen under these conditions? I have my alkyl bromide. The Br is going to come off. I'm going to have a carbocation. That carbocation is going to be attacked, and this is, by the way, the rate determining step of the reaction, by the alcohol to form this thing, which is going to lose the extra hydrogen to another molecule of alcohol, most likely, to give us an ether as the final product, and this is going to be in the form of both possible enantiomers because the carbocation could be attacked from either face. So you're going to get this plus this in pretty much equal amounts. So we're going to get this as the product, a racemic mixture, and the mechanism is going to be SN1. Now notice how a secondary substrate can give us either SN1 or SN2 depending on the conditions of the reaction. The previous example was also a secondary substrate, but that gave us an SN2 reaction because we combined that with a strong nucleophile and a polar aprotic solvent that tipped the balance towards an SN2 reaction. All right, next example. We have a tertiary alcohol with H2SO4 and heat. Is leaving group good? Actually, no. Leaving group is not good in and of itself. It's like OH, and OH could leave to form OH minus, and that's a pretty poor leaving group. However, I'm combining that with a strong acid. What that can do for me is that it can protonate my alcohol, and now that turns into a good leaving group. So leaving group is not good in and of itself, but I'm doing something about it. So like that's fine. Substrate is tertiary, so I know that it's not going to be SN2. That's eliminated right away. Can it do elimination? Yes, it does have beta hydrogens, so it does have hydrogens here and there. Now let's look at the nucleophile slash base. Well, we don't really have a nucleophile slash base. We have H2SO4, which is basically H plus and HSO4 minus. Very, very, very non-nucleophilic H2SO4. So very weak and not nucleophilic at all. Doesn't have steric hindrance, so that is not a concern. And temperature, it shows heat, which would favor elimination, and solvent is probably like water and H2SO4, which is polar and protic. Now let's put all of those together. We already said that it's not going to be SN2. It's also not going to be E2 because we don't have a strong base present. Our base is very, very weak, HSO4 minus, and it's very, very non-nucleophilic. Actually, this is the thing that I was referring to when I said the only kind of practical E1 reactions is going to be dehydration of alcohols. This is an example of dehydration of alcohols. You react an alcohol with a strong mineral acid. It's going to get protonated, form a carbocation, and the carbocation is going to react with HSO4 minus or whatever the anion of that mineral acid is to create an alkene. So the mechanism for this reaction is going to be E1, the only kind of practical E1 reaction that you're ever going to see, and that is going to be the product of the reaction. So to recap, we don't have a good leaving group, but we have acid that makes OH into a good leaving group, so no problem there. Our nucleophile slash base is very, very, very weak and non-nucleophilic, so we know that it's not going to be SN2 and it's not going to be E2. And it's very non-nucleophilic, so it's not going to be SN1 either, so it has to be E1. And actually, that is the way you make E1 feasible. You put an acid in there. This reaction wouldn't work with, say, like HI, because although HI is very strongly acidic, I minus would be very nucleophilic. However, HSO4 minus is very, very non-nucleophilic, and that is basically the thing about H2SO4 and H3PO4. And you could use them to do dehydration of alcohols. Next example. Okay, leaving group is good, no problem there. Substrate is primary, and I know that primary cannot do SN1 and E1, so that is eliminated. Can it do elimination? No, because there is no hydrogen in this position, so it cannot do E2. So only thing that I have to establish at this point is whether that can do SN2. And SN2 indeed seems to be feasible because I have a very strong nucleophile that is not very basic. Not that it would have mattered anyways. It's not sterically hindered. And I have a polar a product solvent. All of these favor SN2, so SN2 has to be the predominant mechanism to give us the product. And that's it. Let's move on to the next. Okay, so is leaving group good? Yes, I have a pretty good leaving group. Substrate is secondary, so I cannot eliminate any reaction or any mechanism. Can it do elimination? Yes, it does have beta hydrogens, so I cannot eliminate any mechanism. The nucleophile / base, it's very strong, but because of the fact that it has a lot of steric hindrance, it's very basic, not very nucleophilic. Like, things that have a lot of steric hindrance are going to be bad at being nucleophiles, because being a nucleophile would mean that you have to somehow approach, like, find this carbon from the backside, and that is going to be hard if you're a T-butoxide. So when you have a strong base and nucleophile, that pretty much eliminates the possibility of SN1 and E1. And since we have a very strong base that is not super nucleophilic and is sterically hindered, I'm going to rule out SN2 as well, so that leaves us with E2. But let's check the solvent. Solvent is T-butanol which is protic, but that's fine because it's not like we are competing between two mechanisms anyway, so that's not going to matter that it's polar protic. So it's going to go towards E2 and it's going to give us an elimination product like this. Alright, let's move on to the next example. Alright, so leaving group is good, yes. This is a tertiary halide. So tertiary halide cannot do SN2, let's eliminate that. Can it do elimination? Yes, we do have beta hydrogen, so we can do elimination. We cannot eliminate E1 and E2 at this point. Nucleophile / base is actually very strong. And strong bases and nucleophiles usually do not favor E1 and SN1, so we can actually eliminate those safely, and that leaves us with E2. And MEO- actually is very basic and very nucleophilic at the same time, doesn't have much steric hindrance, but that wouldn't matter because we cannot do SN2 anyway because it's tertiary. So the fact that it's very basic, it's going to push us towards E2, despite the fact that we have a polar protic solvent, because we really are not competing under these conditions. We have a very strong base. It doesn't matter that the solvent is polar protic. Putting all this information together, that is going to give me an E2 elimination. Alright, next example, and I think this is the final example, yes. Alright, is the leaving group good? No. This is tertiary. Can it do elimination? Yes. Am I doing anything about the leaving group being poor? Yes. I'm combining that with an acid, and that acid, which is practically H+, I-, can protonate this OH and turn that into a good leaving group. So we're solving the problem of having a poor leaving group. And because of the fact that it's tertiary, I know that it cannot do SN2. The nucleophile that I have under these conditions is going to be I-. It's very strongly nucleophilic, not very basic. So that is going to eliminate the possibility of E2. And because of the fact that it's very strongly nucleophilic and not very basic, also eliminate the possibility of E1. So I'm kind of left with SN1. Doesn't have much steric hindrance. And the solvent that HI comes in is usually water. I should have written that. I'm sorry about that. And is polar protic, but that is actually going to favor formation of a carbocation after you protonate your alcohol. And that carbocation can now combine with I-, which is very nucleophilic, to give us this product with an SN1 mechanism. I hope you like this video. If you did, please give it a thumbs up. That's going to help me a lot. Also, consider sharing this video and subscribing to my channel to see more solved problems, tips and tricks, and tutorials. Check out my website at yourokmtutor.com. And until next time, take care.